let's talk about, I am on page 29 in the notes, if you wanted to go there in your notebook. And this stuff is not relatively difficult. It's just kind of doing some stuff that the calculator will do. But the first thing that we're going to talk about are just scatter plots. Now, you've been doing scatter plots forever, okay? In Algebra 1, you had two dots that you put on the XY axis and drew one line through it. So think of the Algebra 1 approach. If you had Algebra 1, you probably had, or geometry, you probably had 2 points that you could draw exactly one line through. Remember that? So that's basically a really cheap version of a scatter plot. And you probably remember the rule from geometry that if you have 2 points that lie in a plane, which 2 points should lie in some sort of plane someplace, there's exactly one line that goes through them. Now, a scatter plot is we're going to have lots and lots of data that take place, and you put something in called the line of best fit. And you might have done a line of best fit in science. We're on page 29 in the notes. So a line of best fit, all it really is, you know, in science, you plotted all your data, you took a ruler, you tried to get the same number of data points above the line as below the line, and you draw a line of best fit. If you picked 2 different points than your neighbor had picked, you would find out your equation would be a little bit different than your neighbor. Okay. Now the nice thing is the graphing calculator does the scatter plots very, very nicely. You would more than likely plug into L1 and L2. L1 would be your X values, L2 would be your Y values. Okay. We're on page 29 in the notes. So that's the long and the short of what we're going to get to, but let's talk about, there are some ideas that come along with scatter plots that the calculator does really nicely for you that works nice, great stuff. So scatter plots use bivariate data. That is 2 quantitative variables to represent the coordinate grid. The purpose of scatter plot is to look at a trend between 2 variables. In this assignment, we will look at scatter plots with straight line linear trends. The scatter plot is shown below as far as the notes go. So you can have a line of best fit. You can have a quadratic of best fit. You can have a third degree, you know, something that does something like this of best fit. You know, a polynomial of best fit. This all comes from gathering data. Now the hard thing is, how much data should you have versus how much will the calculator take? The calculator will take, you know, you could have 3 nonlinear points or 3 linear points, and you could find all different types of equations that those points would share. Okay, but I should do this. We have x-axis, we have y-axis. We tend to use quadrant 1, which has a positive x, comma, positive y value. Now, you don't have to only use quadrant 1. You certainly can use the 4 quadrants of the xy or the Cartesian plane. The scatter plot shows a horizontal axis is called the explanatory data, which a lot of times we call that independent. And then we're on page 29 in the notes. And then you also have the response, which is called the dependent. Okay? So those are just 2 different things. Again, you're creating points that go along with it. You might use, say, distance versus time. So time would probably be on your x-axis, distance would be on your y-axis. as two pretty simple things to deal with. The explanatory variable is often but not always used to explain the behavior or the response variable. The explanatory variable often measured first and is used to explain or even predict the response variable. So you might say, let's take an ACT score. An ACT score might be used to predict how well you would do in college. Okay, so you all know that sometimes if you went to Yale or some other one of the Ivy League schools, that ACT score needs to be pretty much the perfect score. Okay, and they have found that if you show the better a student does on the ACT, the more prepared they are theoretically to go to college. Does that mean that a student that scored a 15 on the ACT can't go to college? No. It's just a lot of colleges use that as a little snapshot of, are you prepared to have the rigor that our college goes with? Okay, so those are just a few things. Other things that you might use is they might say, hey, if we have a really high unemployment rate in a city, would that constitute more crime in that city? And I guess it could. Okay. Things that might change, say, a crime rate would be during warmer weather, we might have higher crime rate. During colder weather, we might have lower crime rate. Okay, if you lived up in North Dakota, you're up there in the winter and it's 60 below zero without the wind chill, you might not have a really high crime rate during that time. Why is that? Well, no one's outside. Okay, everyone's like bundled up, freezing inside, going, I hope the heater doesn't turn off. But does that mean that cold weather reduces crime? Well, I guess you could say it could have some response to that, but it's not necessarily going to be true. So on the page 30, they have different data that they have plugged, but I want to just focus on two of them. So the slope of this line would be positive, while the slope of this line of best fit would be negative. So if you ever hear the term, there's positive correlation, that means the line of best fit would have a slope that is increasing, it's positive. If you have a slope of negative correlation, you have a slope that's decreasing, so the slope would be negative. Okay, and when I say positive or negative, we're talking about y equals mx plus b. Okay, so your m value would be positive or negative depending upon your information. B is the y-intercept, that's where it crosses the y-axis. There are definitely things that you can use for your data to try and predict other outcomes. So that's what's going there. Positive, negative association, got it. Oh, and then if you have something called an R value, it's called the residual, and it's close to positive 1, that means that your data falls very close to the line of best fit you did, and it means the slope is also positive. If you have an R value that is close to negative 1, that again means your data is very close to the line of best fit, but you have a slope that would be negative. So if you have an R value that is close to 0, that basically means you're measuring something that has no linear correlation to it. If you know what, I know most of you have not maybe shot a shotgun, but you might know that if a shotgun is shot and it's full of like, bird shot, and you're standing, let's say, 50 feet away from the side of a barn and you shoot it, it's going to be a big circular pattern of how that buckshot hit. Okay, that would be an R value that is very close to 0. That means there's no, and that's a bad way of representing data because it is just what it is, but I just want you to picture a close to 0 R value. Your data, when you plug it in, would all look like that. Okay, you can't really put a line of best fit, or I guess you could try to put a line of best fit, but once you found the R value, which the calculator will do, will tell you whether the data is good or not. So let's take an example. Let's say we had data plugged in. Does that appear that it's somewhat linear? Yeah. So there's an R value, which is the vertical measure from the line. So if I wanted to do the R value, I would take all of these, how far away from our line we would be, I would sum those all up and find the average. If I went to R squared, just so you know, is the same thing as R times R. Okay, here comes the algebra 1. It forms a square. And that's a two-dimensional look at the data. So I'm going to just draw another. So these would be the R values here. But if I had a line of best fit, and let's say my data is like this basically creates a square. And this is what your calculator is doing, is it created a square. You're taking the areas of the square, adding up all the areas of the square and figuring it out. R and R squared are very much related. Your calculator will generate both, which is very fortunate because in order to, I don't have it right there, in order to find the R value by hand, it's long and tedious. Okay, fortunately the calculator finds it. Be aware, scatter plots collected from data can look like about anything that you dream up. Consider, as we said, data everywhere. That means, hey, I'm not showing any association between this data other than it's not related. To, I have this information that forms a really nice straight line. Let's form a straight line, put a line of best fit. The calculator will indeed solve for you how to get the line of best fit. And I want to bring up my graphing calculator. I just want to walk through how this would work on the graphing calculator. It's thinking, it's coming. All right. So let's do a stat edit. I'm going to clear out this data. I'm going to clear out this data. Okay. Within your best knowledge, tell me your height in inches and the shoe size you wear. Okay? Is that going to make sense? And if you don't feel comfortable giving that information, your height in inches and your shoe size, just say, I'm not going to sell you. And that's okay. Okay? Height in inches,
70 inches, 17.
17. Good enough? Gio?
I don't know how many inches. 5, 6.
5. 66.
Sorry.
66.
And what's your shoe size?
10 and a half.
10.5. Okay. That works.
Oh,
60.
yeah, and I wear 7.
A size 7.
Yep.
A size 7 in girls is a size 5 in boys, right?
Yep. Little feet.
It's okay.
Patriarchy.
Wait, 7 and women?
Yeah, women's shoes are 2 sizes smaller than a guy's. Go ahead.
63 inches.
Uh-huh.
Size 7.
Size 7, so it's a size 5.
Yep.
Okay. Go ahead.
67.
67 and what? 10. Oops.
So, you're gonna be 69.
Actually, I want to try the chocolate crunch one.
And I'm just going to use these 2 rows, not because not the rest of you aren't important. It's just.
You should use tennis too. She should be an outlier.
Oh, yeah. Really
Go ahead. All right, got you. Go ahead.
67 and 8.
67 and 8. Did you already subtract 2 from that?
No.
Okay.
So it's like a men's? Yeah. So it's men's?
Huh?
So it's men's?
Yeah.
5 and a half?
Yeah.
I guess we could have added 2 to all the
that'll
men's.
be what, 6 and men's?
Uh-huh. Go ahead.
70 inches and 11
70 and 11.5. CG?
65 and then I is 6 and men's.
6 men's, okay.
Wait, so I can't do 6 then, because I'm 8 in women's.
Are you the 67 8?
Yeah, yeah.
You're an 8 in women's?
Yeah.
So you're 6. Okay. Go ahead.
68.
68 and 12. Go ahead.
63.
And 5, did you already subtract 2 from? Are you 5 in women's?
Yeah.
Okay, so you'll be a 3. In men's?
Probably like 69 and size 10 now.
10.5, okay. Okay, I think we have enough data. Oops. Did you say 10.5? Okay. So, thank you, these 2 rows, for sharing your information. All right, so we have enough information that we can plot our line of best fit. So we have to go into, and the directions to this are on the very back of these pages. So I'm going to change it from a box and whiskers plot to I want to make a scatter plot. Okay? So notice when it switches, it goes to L1 and L2. We can change it to a square, a plus, a bigger dot, or a smaller dot. It doesn't really matter what you choose. So let me just make sure there's nothing there. I'm going to hit zoom. Oops, I'm going to turn this stat plot off. Oops, zoom 9. So that's our data based on height versus shoe size. Now, of course, the more, if I collected everyone's data in here, we're probably going to get a little bit closer to a better linear regression. Okay. Now, there's one key that you have to remember to turn on the calculator in order to get the R and the R squared value. So what you want to do is, if you haven't done this before, you hit second catalog. I just forgot the name of it. Catalog, where's it at? Catalog. Diagnostics. So I want to turn the diagnostics on. The diagnostics on is going to allow me to get more information. So if I go back and I have a graph, here's my graph. If you go to stat and you want to go to calculate, No longer one variable stats, no longer two variable stats. You want to do the linear regression. Now there's two different linear regressions. There's number 4, AX, where A is the slope plus B, but they also have A plus BX, where B is the slope here. Which is the right one to use? In my opinion, they're both the same. Okay, so I'm going to use number 4 because we're more used to seeing that. I hit calculate. This tells me that we have a slope of 1.06 roughly. We have a y-intercept of negative 61.5, which is kind of ridiculous to think about. We have a height of negative 61. Okay, so there's some data that we don't have to use. But then notice we have an r squared value. That would be where we're making the squares. We have an r value. If you look at the r value is 0.82. So think of this 82 as 82% on a test. Fairly good. That 0.82 might get closer and closer and closer to 1 the more data we plug in with the height and shoe size. Okay? The r squared is always going to be positive. The reason why the r squared is always positive, if I take any negative value and I square it, I get a positive number. Okay? So the nice thing is we have this line of best fit. So I can go y equals vars statistics equation. It's going to plug in that data. I hit graph. It draws in my line of best fit. So then we can interpolate data, which means I'm going to try and make a prediction that's inside of our data amount. And I'm actually going to zoom out once. So if I interpolate, I'm making a prediction inside of my data points. So if I go second calculate, and I want to find a height of, say, 66, someone with a height of 66 inches should have a shoe size of right around 8.5. Okay, 8.6 doesn't make sense because we go to only half sizes. So 8.5 maybe to 9. So that's inside the data. But let's say we want to predict, Shaquille O'Neal. Someone with a phone, tell me how tall Shaquille O'Neal is in inches.
He's 7'1".
85? Is that right? So Shaquille O'Neal is going to be an extrapolated data. So based on our stuff, Shaquille O'Neal at 85 inches tall should have a shoe size of 28.7 or maybe 29. I don't know if that's really his shoe size. I know that Shaquille O'Neal is a big person. But being that this happened outside of our data, this is called extrapolation because it's outside of our data set, but we're making a prediction based on it. Interpolation would be something that's within our inside of our data. Yeah.
The shoe size is 22.
Oh, so we were off. Our prediction was off. But the things that might change that, if we collected more data, our line of best fit might change a smidge, which the more data we have, the more accurate our prediction could be. Yeah. But could you imagine a size 28, 29 shoe? Like that, I don't even know if that's definitely a special order. I don't think you can go over to the DSW. Walk in there. You got size 29? No. Okay. Can I just buy two? Can I buy a size 14 and a size 15, and when I add them together, that's 29? So that's kind of the ins and outs of it. On page 32 of the notes, it does offer the directions of how to plug it into a calculator. But again, friends, if we are doing some sort of activity and you're not quite sure on a calculator how to make it work, then ask me. Okay? Again, I want you to feel comfortable with the technology we're using. I don't want you to be, turned away from it saying, I don't like this because I can't remember it. And nor do I want to have a note card be used up for just the directions of which buttons to push to get on a calculator. So, I would say for tomorrow, or excuse me, this will be, tomorrow is Wednesday, right? So do Thursday, because we have part 2 of the chapter 1 test tomorrow. So do Thursday would be page 139, 140. Okay? And I want to give you time to work on it now so I can help you if anything on a calculator exists for you, which is totally fine. Sound good, friends? All right, let me stop recording.